again, hello everyone, welcome back to the latest lecture session. So let's have a quick recap of what we have been up to in the last couple of sessions and then move on to the aspects that we plan to discuss today. I guess the deterministic approach in greater detail and then the stochastic approach, right. So again, looking at what we have been up to, we have been looking at risk assessment. And before we look at the summary or try to summarize risk assessment, let's try to again recap why we need to look at risk assessment. So in this course, obviously we are talking about remediation of contaminated sites, right. So before I put in time and resources, I need to know, let's say what is the level of risk that this particular contaminated site would pose to my exposed population here, let's say, right. So to be able to do that, obviously I need to be able to come up with risk assessment or conduct the risk assessment here. And obviously we looked at two different cases, one the quantitative and the other the qualitative. Qualitative obviously pretty subjective, right, as in somebody says the risk assessment, the risk posed by this particular contaminated site to the relevant exposed population is very high, low and so on, but that's subjective, right. I mean, depends upon the interpretation or such of which differs from person to the person, from one person to the other, right. So to rule such issues out and also to allow for more scientific analysis when we look at remediation, let's say specifically, we are going to look at, let's say, risk assessment and its quantitative or the relevant quantitative aspects, I guess, yes. And in that context, we looked at four major aspects, I think: data assessment, exposure assessment, right, toxicity assessment, and then risk characterization, I guess, right. So these aspects more or less we looked at them in some detail. But major aspects or take home messages were that we need to look at the uncertainties, let's say, in toxicity assessment and also in exposure assessment, right. But as of now, we have not yet looked at those uncertainties, but we are going to. And then once we look at those aspects for non-carcinogenic risks, we calculate the hazard quotient, right. How do we calculate that? We calculate the intake, right, divided by the reference dose, right. And for the carcinogenic risks, what do we get? We can calculate the slope, pardon me, not the slope factor, but the lifetime cancer risk as slope factor into intake, right. So intake site specific, right, both the intakes are site specific, but these two what do we say standards, or not standards, pardon me, standard values which are slope factor and reference dose, where do we get them from? From the relevant toxicity assessment or from the toxicity studies and so on, right. Again, we discussed that in relative detail again here, right. So here obviously the sum of all the hazard quotients over the different pathways and such, right, we call that to be the hazard index, and similarly here it is a lifetime cancer risk, right. And what are the thresholds? Obviously, if you look at the way that they were set up here, in the case of non-carcinogenic risks, right, what do we see? That the hazard index should not be greater than 1, right. So if it is greater than 1, that means that the relevant affected population has what do we say, a greater than what do we say, acceptable risk, more or less, right. So in the case of lifetime cancer risk, as we talked about it, typically the thresholds are 10 power minus 6, meaning 1 in a million, right. So if the lifetime cancer risk is greater than, let's say, 10 power minus 6, we deem that to be unacceptable, as in the relevant population has a chance of what do we say, contracting cancer, right, say, or additional chance of contracting cancer when exposed to the relevant conditions we have looked at in the relevant scenario, I guess, right. So in some cases, I believe they also looked at the threshold of 10 power minus 4, right. So again, different cases, but typically 10 power minus 6. So these are the thresholds in these two contexts, right. So in that context, I believe we looked at a particular example, as in we started discussing, I believe, kind of soil contaminated, not soil, pardon me, a contaminated what do you say, area. And I think in the example that we looked at, we calculated the risk posed to a particular set of population due to ingestion of or accidental ingestion of soil, right. So in that context, we went through and calculated the relevant values, I guess, right. So today, before we go into further aspects, let's look at a relatively similar scenario, but in this case or in this particular scenario, rather than looking at just accidental ingestion of soil, we are going to look at the other pathways too, right, and try to look at the comprehensive picture, right, or the holistic analysis, I guess. So let me take you to the Excel sheet that I have here, right, and let's just try to understand what we are up to. So it's still the concentrations, chemical concentrations at a particular landfill, and different parameters we have them here. So the body weight, skin surface area, I mean these are from where are they from, let's say, right? Body weight, let's say, depends upon, let's say, the country, the location and such. So typically, let's say, these point estimates, I am calling them point estimates for now, right? How do we arrive at them? Let's say by some data collection exercise from the site, right? So some values, obviously, let's say skin surface area and such, you know, they can be the standard values that were collected in that particular locality or specific to that particular region, I guess, right? But body weight and some of the other values here, let's say, they can be collected from the site, and you know, the relevant point estimates then be arrived at, right? So again, we have different what do we say values that we are going to look at. Water ingested 2 liters per day, I guess. Air breathed, yes. Retention rate of the inhaled air, absorption rate of inhaled air. These are typically conservative estimates, as is the case in most risk assessments, but obviously again there are uncertainties here too, right? So soil ingested, I believe it's 100 milligram per day, right? That's reasonable. Bathing duration, here we have taken that to be 30 minutes, could be greater too, obviously. Exposure frequency and duration, though, here we are taking that to be 30 years here for now, right? Again, we just went through some of the typical values associated with this particular site and the relevant what do we say values for calculation of the intake, I guess, right? So again, this should sound familiar, as in we have the 4 compounds and we have the relevant concentrations in air, both mean and maximum, groundwater mean and maximum, soil mean and maximum, right? In our case for intake, I guess in the example we looked at, we calculate the intakes for both the mean and maximum. So we are going to look at the same case, but for the risks, though, obviously we are going to look at only the case which takes into account the intake at the mean, I guess, right? Or the mean intake value, right? So going through that, right, chemical, and here we are going to look at different pathways. So what are some of these pathways? Let's just try to look at them. So soil ingestion, and soil dermal contact, right? Groundwater ingestion, let's say, yes, and also dermal contact with groundwater, and I believe I have air inhalation out here. So we are looking at 1, 2, 3 and 4 and 5 pathways here, right? So let's look at some of the aspects here. So for each chemical, let's say, so we have the mean and maximum value, I think rate of ingestion, right? And I think exposure concentration, is it? Not really, I guess. This is conversion factor, and the next one is fraction of ingested soil, that is from the contaminated soil. Exposure frequency, exposure duration, body weight, average time and such. So again, depending upon the type of pathway, we have what we say slightly different variations of the generic formulae, and I guess they were or are supplied to you, I guess, right? And here we have the averaging time, and that's calculated as 30 years into 365 days. And why do we have that here? Because in the non-carcinogenic risk assessment, we will consider that the averaging time is equal to the exposure duration. But obviously, if you try to compare that with the case for the carcinogens, you see that we have a different value, and that is because we assume that the averaging time is equal to the lifetime, which is the 70 years, and thus the 25,550 days out here, I guess, right? So again, coming back to what we have, so averaging time, and then the intake, right, plugging in the relevant values, one for average and one for the maximum value, I guess, right? And again, same case for carcinogens and so on. So in here, I guess, obviously we see that the issue here is that the maximum, you know, is greater than the average value by order of magnitude, right? Here we have 10 power minus 7, and here we have 10 power minus 6, right? So again, how do you take this into account in your analysis, though, right? Again, please keep this in mind, because you are going to come back to this later, as in here we have a case of maximum concentration and mean concentration, and thus obviously we end up with mean intake and maximum intake, right? So obviously if I you know, take this further, right, I can thus again calculate a risk assessment based on this intake calculated from what is this now, the mean value of exposure concentration, and similarly for the maximum value of the exposure concentration, right. So how do I compare both the risks in that case, right, or which one do I need to consider in such, right. So again, there are issues obviously involved, but keep in mind that we are going to come back to this later, but let's understand some of the issues at this stage itself. So similarly, I believe for soil dermal contact and such, skin surface area and such, I guess different factors. Again, what are the factors given here? Area of skin exposed, skin surface area, dust adherence, I guess, and effect of soil matrix. So some of the values that you typically see in that particular formula, I guess. And again, we see that we have the mean and maximum intakes for both the non-carcinogens and carcinogens. Again, why do we have different intakes for non-carcinogens and carcinogens, I guess, right? It is because of the way we consider the averaging time, right? And again, same case, I end up calculating it for groundwater ingestion and some other data. Exposure time, we took it to be due to bathing anyway 30 minutes, right. So again, from research paper, I guess the dermal permeability values, right, as in your particular what do we say compound is now what we say in contact with your skin. So you are going to have different dermal permeability values. I think where do we have them out here? Groundwater dermal contact with groundwater, and I think these are the different permeability values, and looks like we took them from a particular research paper. So again, the reason I am looking at this or talking about this in relatively greater detail is that again, obviously there are going to be uncertainties with this value, or there are going to be variations from this value for each person out there. As in, my skin might have a higher what do we say permeability value for a particular compound when compared to your skin, right. So again, but here keep in mind that we are for now only looking at a point estimate. Again, we will come back to this later. So in same case, we calculated the intakes and so on. So then if we calculate the risks, let's see what we have here. So we have the average intake, right, and we have the slope factor, and I guess for carcinogens, chlorobenzene is not being considered as a carcinogen, and thus we have no slope factor. So the risk associated with that is 0. And again, we calculate the carcinogenic risk. Again, this is from just the air pathway, typical example here, right. And again, from here, from the non-carcinogenic risk. So from the pathway of air inhalation anyway, right, we have the carcinogenic risk and we have the non-carcinogenic risk here, right. So obviously I should not have used the term hazard index, maybe hazard quotient at this stage. Hazard index typically looks at the sum of the hazard quotients for all the pathways, I guess. But here obviously we are looking at only the air pathway, or maybe I do have it here. Yes, I do have it here. So for soil ingestion, again different cases. So we have the what do we say now, the risk associated with the carcinogenic risk for soil ingestion, right, and again for non-carcinogens, right. And typically, as you see, the thresholds were 10 power minus 6 as we consider for carcinogens and 1 for non-carcinogens. And from what we can see out here though, right, we see that typically they are relatively lower compared to the threshold though, right. And the sum though, if we look at the sum, the total carcinogenic risk is let us say 1.1 into 10 power minus 7, right, and our threshold is 10 power minus 6. So thus we deem that the level of risk posed to the people at this particular site is acceptable, I guess, right. And if we come back to the hazard index, I guess this is the true way because I did sum up all the hazard quotients. So the hazard index again gives us an idea about the risk posed due to the toxic compounds or the non-carcinogens. So even in that case we see it's 5 into 10 power minus 3, so that's much less than 1. So obviously here from our risk assessment, what can we conclude that for these exposure conditions and concentrations and so on, the risks associated with or to the relevant population are lower than the relevant thresholds or are within the acceptable limits, right. So again, let us say just to understand this system better, we have the relevant risks listed here and in a histogram so that we can visualize what do we say in a better manner. So here we have one particular graph for non-carcinogenic risk, and on one of the axes we have the what do we say different pathways, I guess, right. And here for soil, groundwater and air. For soil we considered both ingestion and dermal contact. For groundwater again ingestion and dermal, and inhalation I mean only for air, I guess, obviously. right. So obviously when I look at this, which pathways typically seem to be posing a greater hazard to me, and typically it seems soil, and also which particular chemical, again that is BEHP, I guess, right. From groundwater, it is typically only the ingestion that seems to be an issue. So while bathing or such, at least for the time taken to be 30 minutes, I guess, right, looks like the risks are remarkably lesser or relatively lesser compared to the risks associated with ingesting or drinking the groundwater, right. So that is what I see out here. So again, how will this help me? So in general, though here the risks were within acceptable levels, right, as in I think here we are talking about non-carcinogenic risk, and if you see the maximum is around 3.5 into 10 power minus 3, and obviously the total risk too was 5.5 into 10 power minus 3. So thus we did deem this particular risk to be within the acceptable level, right. But let us say if it were higher than what do we say, the acceptable level, then what do you need to do? You need to go in for remediation, right. So in that context, let us say when I look at the risk, or understand the holistic picture as I see from this particular graph, let us say, right, what did we look at? We looked at that the soil pathway poses typically greater risk, and then the groundwater ingestion, right. So how would I look at allocating my resources and time? Let us say I would like to look at remediating the effects, let us say posed due to soil and the groundwater here, right. So I would think of treating groundwater and maybe limiting access to what do we say, the soil, right, or contact to the soil, maybe excavating the soil, washing it, depending upon the type of contaminant, I guess, right. So again, this particular risk would then, picture would then help me identifying those compounds which seem to be, which need to be of, or which are of greater concern, in this case BEHP for the soil pathway, and in the case of groundwater, I think chloroform and chlorobenzene, I guess, right. So it helps me identify also the chemicals, let us say that are of greater concern for a particular pathway and such, right. So moving on to carcinogenic risk, right. So what do I have here? Similar case again, and here again the maximum seems to be around 10 power minus 8, or 6 into 10 power minus 8, and as we looked at the total risk associated, it was 1.1 into 10 power minus 7. So again our threshold values are, what's the threshold value? Please, it is 10 power minus 6 again. So thus the risk, since the lifetime cancer risk for those particular exposure or for that particular exposure concentration, right, turned out to be less than the acceptable level, right, which is 10 power minus 6, we deem that or we would think that no remediation is required, right. And thus obviously again, if I just understand the case here though, as you remember, let us say when I calculated the risk, let us say I needed to look at the intake. So in the intake case, let us say if you remember, the average was 1 order of magnitude or 10 times lower than the maximum value. So for example, if I did take what do we say, the maximum value, then the risk would be probably let us say 1 order of magnitude or 10 times higher for this carcinogenic risk, right. So 1.1 into 10 power minus 7 would then end up being 1.1 into 10 power minus 6. So then the risk would be unacceptable, right. So how do I go about understanding this particular scenario now, right, because from the relevant what do we say, concentrations for exposure, I obviously have a mean and obviously a maximum. So the mean value obviously seems to be lesser than the acceptable or within the acceptable levels, but the maximum value is, if I consider the maximum value for the relevant calculation of risk, the relevant risk seems to be higher than the acceptable value. So how do I go about from here, right. So let us say the affected population might say, okay, maybe the average is less than what or is acceptable, but there are a few cases, let us say where the maximum, right, a few cases as in the maximum values where let us say the risks associated are relatively higher than the what do we say, 10 power minus 6 acceptable risk, I guess, for lifetime cancer. So let us say how do I go from here though, right. So to look at this, we are going to look at the stochastic approach. So let us see what that is about. So here moving on, until now we looked at the deterministic approach, right. As in what have we done? We had various what do we say variables, right, body weight typically and so on, and what did we do? We took a point estimate for, or we considered point estimates, right. As in for exposure concentration, we took one particular value or estimated exposure concentration by its mean, and for body weight too, I think we use a particular value, I think maybe 70 kgs in this case. But let us say if I think body weight instead of a person, let us say assume me, compared to the average of what is it 70 kgs that we looked at in that particular example, my body weight is higher, right. So let us say if I look at the relevant calculations, the risk associated for that from that particular scenario and exposure what do we say scenarios, concentrations and pathways would be lower to me. But let us say there are other people out there, let us say maybe not children in the landfill, but there are other workers that are relatively or have lesser body weight, right. Then obviously the risks that are posed to them would be greater, right. So how do I take this into account, let us say, right. How do I take that into account? I am going to look at the stochastic approach, right. So how does this differ from the deterministic approach? I guess it's slightly self-explanatory if I look at the relevant terms, deterministic and stochastic approaches. So here, unlike the case of the deterministic approach, or unlike in the case of the deterministic approach where I looked at point estimates for the different variables, I am going to treat these variables as variables, I guess, right. So instead of having a point estimate, I am going to let us say consider that there is going to be what we say inherent variation, right, in each of these variables. So the exposure concentration, let us say, rather than being one particular value, I am going to try to capture its what do we say variation by looking at let us say its mean and its standard deviation, I guess, let us say, right. And similarly for body weight, maybe for slope factors. If you remember slope factors and such, or reference doses, how have we calculated them, right. We have calculated them by, I believe, looking at or conducting the studies at accelerated, or pardon me, at within shorter periods of time, right, and also at high doses, right. Obviously built in what do we say uncertainties there, because you are extrapolating the results from higher doses to the smaller doses, right, and also from animals to humans, let us say, right, and there are obviously many other such factors and such uncertainties. So here let us say we, instead of using a particular value or a point estimate, and as in the case of this deterministic approach, we are going to have let us say or try to capture what do we say the variation of that particular variable, I guess, right. So obviously mu here is the point estimate here, and sigma the standard deviation will give me an idea about the variation, let us say, of that particular variable, right. So again the major aspect here though is that while as you are going to view it, let us say, or it's going to be able to, or you're going to be able to understand as we go along, right. The major case here though is how do I get these estimates, right, as in capture the spread. This will give me a spread of this particular what do we say variable here, right. So for that obviously I need to collect considerable data, and so in a way this is a minor drawback in the sense that it requires considerable resources or time, and thus obviously data, right, to be able to conduct this or go with this stochastic approach. So how do I get this mean and standard deviation? So obviously I need to take a sample that is representative of the population. Again there are relevant aspects from statistics, I guess, that are involved here, and then take the data from that particular what do we say sample, right, and try to use that to estimate the parameters of what is it now the mean and standard deviation of the relevant population here, right. So for example, let us say there are what we say around 10,000 people affected. Obviously you can't go to each one of these 10,000 people and calculate the relevant data. So let us say you are going to try to take what we say suitable sample, or in this case a sample size of 100, let us say, and see that it's representative of the true population. Take the data from that particular sample size of 100, and then maybe not maybe I guess get the relevant values and the spread of that particular sample, right. So in that case I can go ahead with stochastic approach. So in this case let us move forth and discuss the relevant aspects. So in here we are going to come up with obviously probability distribution functions, right. So what are they about? I guess it's slightly self-explanatory, right. It's the probability distribution functions, right. So again as the name indicates, it's a distribution of the probability, right. So here if I look at a graph, let us say, and before I go for the graph let me consider a scenario. Let us say I have a contaminated groundwater, let us say, and that is due to, and this is the plan view that I am going to look at, and let us say that is due to a particular contamination at this particular source. The groundwater is moving in this or flowing in this direction, and if I look at the plan view, let us say maybe the plume, let us say, is going to be something like this, right, plume, right, contaminated plume. So, if these are my sampling wells or locations, let us say these are my sampling locations, right. So, from these sampling locations, obviously I can get the relevant average, let us say, and standard deviations, let us say, or standard deviation, pardon me, of this contaminated groundwater, the concentration of the contaminated groundwater, right. And so, here what am I going to have on the x axis? The concentration, and here I am going to have the probability, I guess, right, probability. And so, let us say, it should not be normal, but let us say I am taking that to be a normal distribution, but maybe a poor way to understand that. So, this would give you an idea about the probability that the concentration, let us say, would lie within two particular values, let us say C1 and C2, and the probability that it would lie within these two values would be given by the area under this particular probability distribution function, right. Again, that is just for your understanding or sake of understanding, I guess. But let us say, if how do I calculate that though? Let us say, right, what is the probability that the concentration C is between C1 and between C2, right. What is that? This is the integral of that particular probability distribution function, right, say from C1 to C2, right. That is what is this particular aspect about? It is nothing but the area underneath that particular probability distribution function, right. So, again, how can I calculate these probability distribution functions now? Let us look at that particular minor case. Let us say there are different what do we say number of, or n number of events, let us say. So, probability for particular case, after I order them, I am going to rank them or order them, let us say, right, and then let us say what can I do, how can I calculate the probability, let us say the events in the my bin, events in my bin or in the bin by the total number of events plus 1, obviously, I guess, total number of events, right. And by the definition of probability distribution function, how will I get that particular probability distribution function? Is going to be nothing but the probability that I calculate here by the relevant bin size, right. So, from that I can calculate the probability distribution functions here, right. So, obviously, there are ways you can go ahead and estimate or come up with these probability distribution functions, and typically there are different what do you say distribution functions. So, let us look at some of the generic examples, let us say. So, here it is uniform, let us say this is the uniform distribution, but typically or rarely do we get such particular cases. For example, let us say if I consider the body weight of all the students in my class, let us say, or the students enrolled in this course, let us say, right, what would it be? Would it be a uniform 70 kgs as I considered it to be the case in or estimated it to be the case in the previous example? Not really, right. So, if I look at that, plot it and so on, right, say I am going to have something like a normal distribution, right, say, right. So, the mean might lie around 70 kgs, but the standard deviation, right, which will capture the spread, right, plus or minus sigma, I think captures 67% or so of the data, right. So, this sigma will give me an idea about the spread of this particular data from the mean, let us say, and mu will give me an idea about obviously this particular point estimate, the mean or mean, right. So, mu and sigma in this case, and this is the case for probability again, and or you can use this probability, and bin size, if I consider that as in body weights from 30 to 40, right, what would be the probability? The integration of this particular case from 30 to 40 body weight probability distribution functions, right, and body weight, let us say, right, or the area within or under this particular graph, right. So, again typically we come across in our case anyway normal and log normal distributions, right. So, we come across normal distribution, which is what we have here, a case here, and a log normal distribution, So what do I understand by when someone says a particular variable is log normally distributed? It means that the natural logarithm of that particular variable has a normal distribution. For example, let us say if I have a variable x and there are different values, let us say, right, this is not normally distributed, but if I take the natural logarithm of x, let us say, and then have the relevant values, these values are going to be normally distributed, right, and then I am going to call this particular distribution or variable x to be log normally distributed, right. So in this context we are going to look at a particular example, right, but since I am running out of time, we are going to look at the relevant aspects in the next session. So again, a quick recap of what we have been up to, right. We have thus far looked at the deterministic approach, and we obviously see that it is relatively easier to calculate that, right, relatively less time and resources obviously, but the issue here is that you are getting a point estimate, since obviously you are using point estimates for the different variables, right. And in that context we saw that, let us say, the risk that we calculate for the relevant cases for air, groundwater and soil ingestion or dermal contact, we saw that if we took the mean value, right, we get a particular risk, and if we took the maximum value we get a different risk obviously. And in that context we saw that for carcinogenic risk the value turns out to be higher if we consider the maximum value, right. So to understand these effects and also understand, or not understand, I guess, consider the effects of the uncertainties in, let us say, coming up with values for slope factor and so on, right, we look at the stochastic approach. And in that context we have looked at some of the variables and how they are going to be distributed, and typically we look at probability distribution functions, let us say, and we just mentioned that we typically look at two cases, normal and log normal, and let us see how we are going to use this information to be able to calculate the, or take the stochastic approach further, I guess, right. And I guess with that I will end today's session, and thank you.